When simulating thin models, it's often useful to model them as 2D surfaces in the 3D space. For instance, you could use a triangular mesh and assume that there's no deformation in the normal direction. That's one of the typical ways that people do cloth simulation. Standard thin shells often feature large clusters of non-deforming parts, both with or without wrinkles. In this example, you can see rigidly moving regions and local deformation. See how the two ends express very little deformation, while wrinkles form near the crease in the center. We will explore an adaptive method to target these regions, fully preserve curvature, and allow deformation where needed. One of the effective methods to speed up the simulation of shells is to adaptively remesh the models so fine details are simulated in high curvature regions. For instance, ArcSim starts with a coarse model and adaptively inject high-resolution details where wrinkles are forming. There's post-process refinement that generate wrinkles after running a coarse physical simulation. This is usually done by machine learning or data-driven methods. There's also sleeping methods that remove degrees of freedom when they are deemed unnecessary. You could argue that the original adaptive rigidification is a generalization of that concept. The previous work on adaptive rigidification focused on elastic solids. The core idea was that we can monitor strain rates, and when they satisfy a threshold, then we can tag the elements for rigidification. Rigid bodies are built from sets of connected components with element tagged for rigidification. An oracle then predicts the formation of rigidified parts to know when to let the elements become elastic again. This method not only allows coarsening of static meshes, but also rigidly moving parts like the tentacles of this octopus. Shells are particular because you can have bending without stretching and stretching without bending. To end those stretches, we can naively use a similar process as the rigidification in 2D simulations, though this does not account for the bending deformations. Only looking at the membrane deformation would potentially lock the triangle flaps into place, even if they're meant to bend. We need a good measure of the bending deformations. Adaptive rigidification is an interesting fit for thin shells as it is independent of the meshing. This means you can have a fine model preserving the rigidly moving deformed state elements like wrinkles. However, the original adaptive rigidification's oracle fails to detect light contacts that should generate bending, like in this scene. We need to modify the oracle to allow bending deformation and cheaply diffuse the motions from the bending components. In our contributions, we derive a convenient membrane to bending equivalence that allows us to set a single pair of thresholds for both the bending and membrane deformations. We enhance the oracle with contact diffusion to help the propagation of bending deformations. We fix one of the major complaints that adaptive rigidification had, where the condition number would go up for mixed rigid elastic bodies. We do so by introducing scaling techniques. And obviously, we adapt rigidification to work for the simulation of shells. As opposed to remeshing techniques that start from a coarse model, we start with a fine model and adaptively reduce the system. Likewise, we can potentially completely reduce high curvature regions to just a few degrees of freedom. This is not something possible with standard remeshing techniques, as it always requires a certain number of elements to realistically represent a curve. Monitoring the membrane strength is essentially the same as doing adaptive rigidification in 2D. If the Frobenius norm of the strain rate of an element is below a threshold for a few steps, then it can be tagged for rigidification. Elements tagged for rigidification must have both their per-edge bending threshold and their membrane threshold satisfied. We do a breadth-first search to find connected components, and each component becomes a new rigid body. To monitor bending, an intuitive solution is to look at the dihedral angle, the per-edge angle between your elements. In our case, we use triangle meshes. Of course, this could trivially extend to quad meshes. Almost all shell simulation use this measure for the computation of bending energies, and therefore it can be reused cheaply for the purpose of evaluating the bending rates. However, these angles are discretization dependent. If you look at different discretizations of a surface, you will see that a coarse resolution will have sharp angles, while a fine resolution will have nearly flat angles. Because of this, monitoring the dihedral angle rates would yield wildly different results for different resolutions. We want to be able to set a single threshold that works regardless of the discretization of our models. You are unlikely to always work with perfectly uniform meshes and certainly don't want to start picking threshold for each individual parts of your mesh. So instead of directly using the dihedral angle rates, we compute the curvature rates. For the same model with different discretization, the curvature remains mostly consistent. It is defined as the inverse radius of the osculating circle, which can be evaluated at any point on the curve. We then use the discrete per edge curvature rate as our measure for the bending deformation. While the discrete curvature is an approximation, the error is reasonable and the measure is used solely to detect rigid elastic transitions, not the physical simulation. If we try to model a circle with discretized triangle flaps as shown by the red lines, then for large triangles we get the curvature value that is a bit off. As we discretize the triangle into smaller elements, like this, the discrete curvature tends to converge toward the actual curvature value, in this case, 1. We notice that even with large elements, the discrete curvature remains reasonable and within a 20% range from the expected value of 1. We can set the membrane threshold and use our equivalents to automatically pick a bending threshold. Assuming you have a line segment that is either stretched with extension ds or wrapped around a circle with bending distance db, then we can look at how a horizontal bending distance would affect the curvature if the bending distance is equal to a stretching distance. From this, we obtain a formula with a bending threshold tau b for a given membrane threshold tau m. In an actual simulation, we choose the y parameter to be the diameter of our model. This makes the equivalence not just resolution independent, but also scale independent. And this is important because the curvature itself is not unitless. It has a unit of 1/meters. Not accounting for numerical damping, the rigidification patterns are the same across resolutions when using the curvature rates. Sometimes it's reasonable to monitor the dihedral angle rates directly. For instance, this bunny is coarsely discretized and would benefit from this. Note how the elastic color is brown here to look like one of those chocolate bunnies. You know, the ones that are hollow, so when you bite them, you're disappointed? Same thing here. It's made out of shells and disappointing because it's way too coarsely discretized. See how the ears and feet are extremely sharp. For models with sharp angles, the radius of the osculating circle is going to be increasingly small. Because of that, the curvature value is going to be large and a small change in angle will cause a large change in curvature. This can generate some undesired elastification, though we argue that this should not be an issue in reasonable simulations. The majority of the deformation is the bending at the attachment point, so we would expect rigidification at the other end, and this is what we see here. So quality is preserved regardless of the material properties. Like the original adaptive rigidification, our preconditioner for the oracle is assembled from the Laplacian of the mesh. We do a single precondition conjugate gradient iteration to approximate velocities, from which we compute the approximate membrane strain rates. Of course, we now also use these to compute the approximate curvature rates. The core of the oracle is similar to the original adaptive rigidification. For existing contacts, we can use the warm start values, which should be very close to the actual solution. For new contacts, we solve them as elastically decoupled bilateral constraints. But this is not enough for shells. The original adaptive rigidification oracle fails to properly identify regions of elastification on tiny new contact that cause bending deformation. This is likely due to poor local propagation of the bending deformation, as the preconditioner is similar to the membrane stiffness, not the bending stiffness. Because of this, the strong membrane coupling could prevent good local convergence when the bending stiffness should be dominating. We tested many heuristics, but to us some stand out more than others. Let's dig into them. We tried to locally diffuse the impacts with a discrete Laplacian operator. This allows local diffusion of impacts with respect to the contact directions. You can build this operator using the uniform Laplacian formula, where Aleph is the set of neighboring vertices. Visually, you can think of this operation as the application of a small per-edge filter, where vertices not in contact receive a positive impulse, while vertices in contact will receive a negative impulse scaled by valence. We get a similar result by doing a CG iteration for local propagation before the oracle's PCG iteration. The core idea behind this approach is very similar, but it needs to go through all the degrees of freedom as opposed to the contact filter. We also note that contact-heavy scenes will see diminishing returns from using this filter. We only use the heuristics for new contacts as they will likely create larger change in velocities than the old contacts. Note that only a small region of elastification on first contact is enough to preserve most of the momentum for visual consistency. We only run the oracle once before the Newton solve. To simulate mixed rigid elastic bodies, we use a kinematic mapping G where gamma maps the rigid body linear and angular degrees of freedom. We can then solve for the change in velocities using the reduced linearized system for each Newton step. Mixing rigid and elastic bodies can create poorly conditioned systems as it increases the mass ratios. Likewise, stretching a model can quickly raise the stiffness, again making the system poorly conditioned. We note that simply scaling the system can reduce this conditioning problem and sometimes make the adaptive solution better conditioned than the elastic system, especially when rigidifying away poorly shaped elements like the ones in this stretched model. Using Jacobi scaling already greatly helps, but using the Curtis scaling makes the adaptive system's condition number competitive with the full elastic system, and often better. In practice, iterative solvers are often used to obtain fast approximate solutions. When using adaptive rigidification, we already have a nice preconditioner that can be used for a preconditioned conjugate gradient solve. The condition number is important for accuracy, especially in iterative solvers where the problem is not solved to convergence, so scaling will help. We also notice that when the system is fully rigidified, it might be advantageous to roll back to direct solves, like here. Strain limiting can also benefit rigidification as elements stretch to their limits for a few steps have their strain rate greatly reduced. Hence, the rate of rigidification can increase in stretched regions. The overhead of adaptive rigidification is negligible even when fully elastic. However, rigidifying just a few elements can already lead to significant speedups. This is a simulation with only one Newton iteration per step, but of course cranking up the number of Newton iteration would further increase the speedups. That is because the rigidification process only requires a linear pass prior to the solve. You can see that the regions of elastification mostly target where the bottle hits the tablecloth, but also where gravity creates deformation. Depending on the thresholds, adaptive simulation can either perfectly match the elastic model or diverge to some extent. Pushing the threshold too high can potentially cause some visual artifacts. Here we notice the same wrinkle patterns appear in both meshes, but the adaptive mesh spins a bit faster. This is likely due to more continuous contacts across rigid bodies. There are also nice rigidification patterns in non-deforming regions, like the top of the spheres or parts of the cloths lying flat on the ground, like here. Here is a toy dancer with a stiff plastic crinolet-like dress. In this example, the adaptive method oscillates between 1 and almost 2 orders of magnitude faster than the elastic simulation. As a reference, 2 orders of magnitude is 100 times faster. The dress features local elastification targeting the deforming regions, followed by quick rigidification as the dress stops deforming. While we've showed many stiff materials, this also works splendidly for softer shells. Here we can see some large and fine wrinkles rigidifying, as well as rigidly moving chunks of elements. So we have presented a way to choose both the bending and membrane deformation thresholds at once with our equivalence. This alleviates some of the threshold tuning effort. We enhance the oracle for the propagation of small contacts that cause bending. Other types of preconditioner could also produce interesting effects that would be worth testing in the future. We improve the conditioning of our mixed system using scaling methods. This can also be used for the adaptive rigidification of elastic solids, as its result on the condition number should be the same. All of this is done while still benefiting from the large improvements in speed due to our rigidified systems. We also have an industrial partner that does surgery simulations. Shells can be used to simulate thin body parts like ligaments. Of course, the deformation is local, near the operation, so adaptive rigidification is an interesting fit for this type of simulators. We believe that there are more opportunities for extensions that could greatly benefit simulation of shells, like allowing both remeshing and rigidification at the same time. Both methods target different regions of the mesh and should be complementary. We are also working on ways to completely get rid of the threshold selection for seamless coarsening of meshes, and are exploring options for massive parallelization of the solves.